All right, here's part 2 of the solutions for Unit 2, assignment number 2. Here we've got a position time graph, and we're going to make a motion map with one dot for each second. So we're just reading this information out of this graph and putting it in our motion map. So at time 0, we are at position 0. So that's my first dot. At time 1, we're at position 2. So this is 0, 1, 2, 3, 4, 5. That's position 2 right here. You can see if you were tempted to put a dot here, we have to respect the fact that this is going 2 meters in that first 1 second, and that's where it is. So connecting this to math skills that I'm sure you have, we're just basically reading points out of this. At time 2, there's my time 1 there. At time 2, I'm at position 4. At time 3, I'm also at position 4. So I'm going to stack that here because I want to show that I'm not going anywhere. I'm going to move it down here because in case it starts moving again in the other direction, I have some room to do that. That's time 3. And then at time 4, I'm now at position 3, going back the other way. Time 5, time 6, and time 7. I make it back here. And then I'm going to put my arrows in that go halfway to each dot. From here to here, I'm not going to make an arrow here because the arrows we want to represent motion. And here, from time 2 to time 3, it just stayed at the same position. That's the graph of something here, position versus time that is not moving. The position is constant. So I'm not going to draw an arrow there. Here, my arrows going this way. Whether you put one on this dot or not, I wouldn't worry about that too much. And the labeling of the times, if it says clearly here that we're doing 1 dot for each second, you wouldn't have to put those in there, but I think it's maybe helpful, at least now that we're just starting to learn how to do these, to put those in. Okay. Describe the motion in words. We'll say the object, whatever it is, moves forward from position 0 at 2 meters per second. That's the slope of this, rise over run, at 2 meters per second. It does that for the first 2 seconds. Seconds, sorry, spelling. And then for the next second, it stays still. Stays still, remains motionless, whatever you want to say there. Stays still for 1 second. And then moves at 1 meter per second in the negative direction for 1, 2, 3, 4 seconds. There's my verbal description of it. It might be possible to do it in fewer words than I did there, but like that. Okay. Now we're starting with a motion map, and we're going to make a graph. So exactly like what we just did, except I have this information, and I need to go to here. Now, I've seen students sometimes struggle with, like, where does this motion map start? It starts here, and we know that because of the flow of the lines. Like, you can't ever go against what the little arrows are doing. So I'm starting here. This has to be at time 0. Has to start there. So at time 0, position 1, 2, 3, 4, 5, Time 0, I'm at position. Make sure that you're all the way back to here. The graph does not start here, it starts on the axis at time 0. And then so for times, this is time 1, 2, 3, 1, 2, 3, and then 4, 5, it's staying in the same place, and then continuing 6, 7, that's time 7, we're back to position 0, and then tick, tick, 2 more ticks of time, we're going there. If you wanted to check to make sure you're at 9, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we're in the right spot, and now it's moving forward 2 meters, and 2 more meters to end at position 4. And then we can just trace through what we did there. Describe the motion of the object in words. Object starts at position 5 meters and then goes in negative direction at a speed of 1. That's the slope of this. You can see it's going 1 meter per tick at 1 meter per second. Does that for 3 seconds. If you're looking at this and thinking, wait, I thought there were 4 dots there, we're talking that a second is the space between this. This is 1, 2, 3, right? You can see that here also. It's 3 seconds from 0 to 3. Stops for 2 seconds. Continues in negative direction at 1 meter per second for 2 more seconds. 2 more seconds. Sorry, you can read my messy writing there. That says 2 more secs. And then 2 more seconds. And then stops again for a couple seconds. And then trying to write faster than my brain will work. Then moves forward, positive direction you could say there, at 2 meters per second, 2 meters per second for 2 more seconds. All right. And then this is the first time that you're doing this, sketching a velocity time graph. So let's see. What's happening for the first 3 seconds is the velocity is constant -1. It's constant -1. So it's constant at -1. This is not a graph of position. This is a graph of how fast it's going. Its speed, if you were watching the speedometer of this thing, for those 3 seconds, it's going -1, still -1, still -1, still -1, all the way up to there. And then for the next 2 seconds, it's stopped. So if you look at the speedometer, or the velocity meter, which is going to tell us negatives when it's negative, it's at 0. And then for the next 2 seconds, we're going -1 again. And then for the next 2 seconds, we're stopped again. And then for the last 2 seconds, we're going positive 2. So that's an interesting looking graph. That's what our velocity time graphs are going to look like when we have something that's going at constant velocity, different stretches. And if you want to connect this to other things you know, like math things that you know, the slope of this right here is -1. The slope of this is 0. So we have it at 0. The slope of this is -1 again. Slope here is 0. And the slope of this for the last 2 seconds is 2. All right, overhead snapshot of Dorothy and Toto walking along the yellow brick road shown below. So here is Dorothy start and end here, and then Toto's running around all this. I don't know what that is. It's kind of like a toilet, but I'm not really sure what that's supposed to be. Something, maybe it's a tree, something that Toto is running around. I guess a tree is kind of like a toilet to a dog, so whatever. So from start to finish, who travels farther? Justify your answer. Well, distance traveled, it's Toto. Toto covers more distance. And the justification, I think I'm justifying it by saying that Toto covers more distance. You can just look at that dotted line. Dotted line. Path is longer. Who's farther from their starting point? So here's Toto's start and end. So Dorothy is farther from her starting point. I don't know how we can justify that other than saying Dorothy is a greater distance from her start and Toto from his start. And then here, develop 2 different definitions for measuring how far something travels. So the suggestion is here, thinking about these, there's total distance, which is exactly what it sounds like. And then I'm going to tell you the physics word that we're going to use that only cares about the difference between where you started and where you ended, and it doesn't care about the total path. This is displacement, which is equal to your end position minus your starting position. It's just the difference between where you started and where you ended. And if you're thinking, well, why do we need 2 different definitions for that? There are some situations where this is what you would care about, and there's some situations where this is what you care about. I'll give you an example. Let's say you are in the business of renting cars to people. If you're the person who's in charge of like maintenance and like how long cars stay out on the rental fleet before you get rid of them and stuff like that, then you care about the total distance that a car traveled, right? Somebody picks up a car and they drive it around, they have the car for 2 weeks, and then they bring it back. And you care about the total distance, right? They picked it up from you and they're going to bring it back to you. But what you really care about is the total distance that they drove that car around, right? Displacement, on the other hand, if your job at the rental car company is to make sure that the car is in the right place for pickup of the customer and then pick it up from them when they're done, the only thing that you care about is the ending position and the starting position. And it's not your job to care about how many total miles they put on the car. You're just like, okay, you're picking it up at the airport in D.C., and then you're going to drop it off at the airport in Roanoke. Okay, so all you care about is those. And whatever happened in between doesn't matter to you. There's lots of other examples I could give, but that's one. All right, there you go.